First thing that we're going to do today is we're going to turn this generalized cubic equation of state into a cubic equation with respect to the compressibility, or in terms of the compressibility. So first things first, we have our generalized cubic equation of state right here. And what we want to do is we want to end up converting it to this compressibility factor, which we label as PV over RT. So in order to get this left side of the function equal to PV over RT or Z, what we're going to end up doing is we're just going to multiply both sides by RT over V, or sorry, V over RT. So let's do that really quick. V over RT, and then this entire thing is also going to be multiplied by V over RT. So what we end up getting here is PV over RT is equal to, if we multiply this one by V over RT, what we're going to end up doing is we're going to end up canceling out the RTs, but let's just write it all out for now. So we're going to go RT over V minus B times V over RT minus this entire function here, V, let's just rewrite this out at the bottom. V plus sigma B, all under coefficient A. This is also going to be multiplied by V over RT. And so what we end up having here is this is going to be equal to Z. And so we get Z is equal to, these RTs are going to cancel out. And so what we have is V over V minus B, or let's just write that out first. So we have V over V minus B minus AV over the entire bottom. Epsilon B, V plus sigma B times RT. So if we go ahead and further simplify this, we can go ahead and divide the top and bottom by V. So we get Z is equal to 1 over 1 minus B over V. And minus, what we can end up doing is pull out these V's here. So we get AV over, pull out a V here, pull out a V here. We get a V squared. So it's going to be, let's go RTV squared times 1 plus epsilon B over V, and 1 plus sigma B over V. And then, so we can go ahead and cancel out these V's. And so this is just going to be to the first power. Make sure you can see all that. That'll be to the first power, so Z equals 1 over 1 minus B over V minus A over RTV 1 plus epsilon BV 1 plus sigma BV. So now the next step in our algebraic process here, what we're going to end up doing is we're going to go back to the definition of the compressibility factor, which is, remember, Z is equal to PV over RT. And let's go ahead and get this in terms of V. So V is equal to ZRT over P. And let's use this equation. We're going to go plug that into every V that we see in our problem here. So let's go ahead and do that. So now this one equals 1 over 1 minus B over V, or if we rewrite that, it's going to be BP over ZRT, and minus A over, so V is 0T over P, so let's go ahead and get that P up to the top. So it's going to be a P times, we have an R here and a T here. We have an R here and a T here. So it's going to be R squared T squared times Z. And we're going to do the same thing for this. It's going to be 1 plus epsilon BP over Z RT. And same thing here, 1 plus sigma BP over Z RT. So the next thing we're going to do here is we're actually just going to make a couple substitutions just to make this a bit more readable. And so the first substitution that we're going to make, we're going to call this variable beta. And beta is going to be equal to BP over RT. And then we're going to have another variable Q, which is going to be equal to P over BRT. So once we make those substitutions in, what we should get is Z is equal to 1 over 1 minus, remember, BP over RT, that is beta function right here. So we're going to get beta Z minus, if we multiply Q and B together, what we end up getting is actually this R squared T squared. So what we end up with is this Q beta over Z times 1 plus, remember, BP over RT. So it's going to be our epsilon beta over Z. And then 1 plus sigma beta over Z. Settled in, oh, actually, wait, we don't need that. Z, whoops. Yeah. So now that that's all settled in, what we're going to end up doing is we're actually going to divide both sides by Z. So we're going to divide all of that. So when we go ahead and simplify that, what we have now is 1 equal to 1 over, this is essentially 1 minus B over Z times Z, so it's going to be Z minus B minus QB over Z plus epsilon B, Z plus sigma B. And let's go ahead and get our common denominator out here, right? So in order to get a common denominator, we just need to multiply this side by Z minus B. So if we do that, Z minus B over is equal to, or sorry, Z minus B times Z plus epsilon B and Z plus sigma B. And we just go ahead and start distributing this out. So if we were to do that, I'm just going to go off to the side here. Let's just see if we did Z and epsilon B and then Z here and sigma B, we would have Z squared plus Z epsilon B plus Z sigma B, and we would have epsilon sigma B squared. So if you were to further simplify that down, what we essentially have is Z squared plus ZB at epsilon plus sigma plus epsilon sigma B squared. Epsilon sigma B squared. So let's go ahead and make that adjustment. Epsilon plus sigma plus epsilon sigma B squared. So now that we've derived this common denominator that we're going to have, what we can do is we're going to go back to this original equation and we're going to go ahead and multiply everything by that factor. So in order to get this fraction equal to this fraction, we need to multiply the numerator by z plus sigma b and z plus epsilon b, z plus sigma b. So that's going to be like this. So let's just, I think we might need a bit more room. Yeah. So we'll have z plus epsilon b, z plus sigma b. To get these two equal, we're going to have to multiply the numerator of this one by z minus b. So that's going to be minus qb z minus b. And then in order to get this numerator or slash denominator equal, we're just going to have to multiply by this factor. So we're going to have z minus b z squared plus zb epsilon plus sigma. I'm going to have to move that over a little bit. Come on. There we go. Going to move that over. And that last part is plus sigma b squared. And so now we've essentially gone and set up this system for us to go ahead and simplify. So now that we have this, I'm actually just going to rewrite this a little bit. So I'm going to have a z minus b. I don't like that. Z minus b z squared plus zb epsilon plus sigma plus epsilon sigma b squared is going to equal, remember that this is just equal to that, so it's going to be z squared plus z bz, or z, no, zb is good, let's just keep it consistent, plus z b epsilon plus sigma plus epsilon sigma b minus qb z minus b. So now that we have this long mess of a solution here, what we can end up doing is we can go ahead and try and convert it into the cubic form, which looks like z cubed plus c1z squared plus c2z plus c3 equals 0. So that's our general cubic form right here. And so in order to try and simplify this down into the cubic form, what we can do is we can create a table of sorts, right? So I'm just going to use my ruler here, just get some straight lines. How do we change the angle on you? Okay, guess no ruler. So let's go ahead and have a z cubed column, a z squared column, a z column, and a 1 column. And these will serve as our, this table will serve to find our coefficients for each term. So let's start here. So we have z and z squared, so we're going to have z cubed, the coefficient is 1. Then we're going to have z, and this z squared b e plus or epsilon plus sigma. So in z squared, we're going to put beta epsilon plus sigma. Let's go to this third term, and that's just going to be a z term, so that's going to be epsilon sigma beta squared. If we multiply out this negative b, that's going to be negative bz squared, so minus b. Then we go on to this next one, and that's going to give us negative b squared, so minus b squared epsilon plus sigma, right? Double check. And then negative b times that one is going to give us negative b cubed in R1. So negative b cubed epsilon sigma. And so since this, we're kind of keeping us like the positive side of the function, we're going to go ahead and make sure that all of these are going to be negative since it's on the other side of the zero. So let's go ahead and do our same little shtick. We have a z squared, z here, and a 1. And we also have this one here. I'm just going to expand this out into minus qbz plus qb squared, right? So this first one, it's going to be minus 1 minus b e plus sigma and minus e sigma b epsilon sigma. And for this one, this is a z, it's another z term, so it's going to be minus negative qbz, which is going to give us plus qb minus qb squared. So now if we go ahead and rewrite our function in the term of cubic form, we're going to end up with z cubed plus beta epsilon minus sigma minus beta minus 1 z squared plus epsilon sigma beta squared minus beta squared epsilon plus sigma minus beta epsilon plus sigma plus q beta z, and then our constants are going to be, oh, come on. And then it'll be, we'll pull out the negative and then make all the things in plus. So b cubed epsilon sigma minus b, make sure you can see that. Come on. Trying to make sure you guys can see my screen. Okay, b epsilon sigma plus q b squared. So in terms of our cubic form general equation of state, this is what that is going to look like. So now let's talk about finding roots, and we're going to use these statements in Python to try and get these roots for us. So initially, let's look up here, right? We have this conjecture where it says that if we have a cubic function in its standard form, which is listed up here, then we're going to end up having to calculate a Q and an R here that are defined by these two. And depending on that combination of Q and R, come on, we will calculate a theta where if R squared is less than Q cubed, then we're going to calculate a theta and our roots are going to be based off of that theta value. Um, if R squared isn't less than Q cubed, however, we're going to go another route where we calculate this A, and based on the A, we're going to calculate a B value. And based on those two values, we're going to calculate our three roots using this as such. So I'm going to toss this up on my other monitor. And let's go ahead and get started with our code. So for this one, we're not going to need to import anything too crazy. We're just going to import numpy as np. And that'll make sure we have our np library. Now, the first thing we want to do is if we look back over here at our whiteboard, we want to go ahead and we want to calculate Q and R based on our original function. So let's go ahead and get a function called cubic roots with inputs A, B, and C. Ooh, C. And we're going to have our Q. Let me toss this up on my other monitor. We're going to get Q is equal to A squared minus 3B all over 9 minus 3B. Going to put all of this over 9. That's our Q. For our R, we're going to do 2A squared, so 2 times A cubed, sorry. 2 times A cubed minus 9 times A times B. A times B plus 27C. So let me put this in parentheses. Plus 27 times C. And that should all be over 54. Right? So now within this function, we're going to have to create our if statement based on our condition that R squared is less than Q cubed. So let's go ahead and create our if statement. So if R squared is less than Q cubed, then we are going to calculate a theta value. So theta is going to equal the cosine inverse, so np.arc cosine of r over cube root of q, or sorry, r over square root of q cubed. So r over np dot square root of q cubed. Hold on. Right? So that should get us our theta value, and then we can go ahead and calculate our x1, x2, x3. So x1 is going to equal, let's see, negative 2 times np dot square root q times cosine of theta over 3 minus a over 3 np dot cosine. And then our x2 and x3 actually look quite similar to that. So, oh, come on. I'm just going to copy paste this line down. So x2 is just that, except we're going to add 2 times np dot pi. And then for x3, we're going to do kind of the same thing, except we're going to subtract np 2 times np dot pi. It's 2 times np dot pi divided by 3 minus a over 3. That should give us our roots. Just going to double check, make sure everything is right. It looks to be. So for our first condition where r squared is less than q cubed, that is going to be how we find our roots. However, now we have this other situation to deal with here, where we have the opposite. If r squared is not less than q cubed, instead q cubed is greater than r squared. So we're going to have to go through, calculate this a value. Based on that a value, we'll have a b value, and based on that, we're going to find these 3 roots. So let's go ahead and do that part next. So let's go get our else statement. Else, we're going to have come on. Else, we're going to have an a value that is equal to negative r plus np dot square root of r squared minus q cubed. And that is going to, let me just make sure that my parentheses are right. Okay, that's that parentheses. Okay, and all of that is going to be put to the 1/3 power. Essentially, we're cube rooting that. So after that, we're going to have another nested if statement where if a is equal to 0, then b is also going to equal 0. So b is equal to 0. Else, else b is going to equal q over a. Right? And then based on that, we're going to exit our if statement now. We're going to calculate our 3 x's. So now x1 is going to equal a plus b minus a over 3 I'm actually just going to make sure I put all this in parentheses as well. Just can never be too sure. Minus a over 3, our x2 is going to equal negative 1/2. So times a plus b minus a over 3 plus, we're going to use imaginary numbers, so np dot I, and it's going to be root 3, so np dot square root 3 np times square root over 3 over 2 times a minus b. And that should give us our other x root, which is going to be an imaginary root since we are in that imaginary plane. And the third root is going to look very similar to the, third root is going to look very similar to the second root, where we are just instead of adding that imaginary portion, we're going to subtract the imaginary portion, right? And then we're just going to get our function to return x1, x2, and x3. And that should be pretty much it for our function. Now, just to make sure that whatever we wrote down actually does work, we can go ahead and create a test case scenario where we're creating some polynomial by the name of p, and we're going to set that equal to an np function that creates a polynomial based on creates a polynomial for us based on the roots that we give it. So it's going to be with this syntax from roots. And we're pulling this from the NumPy library. And what we're going to do is we're going to import an array. Let's just go simple. 1, 2, 3. That's our array, p, and it should give us a polynomial based on that, based on the roots that we gave it. So now we see that we have a values of -6, b value of 11, and c value of -6. So what we're going to go ahead and do is call back our cubic roots function. And we're going to use these values that we found. So we're going to have -6, we're going to have 11, and we're going to have -6. And if we run that, then yeah, we do get those same roots that we have ended up with, which means that our function is all good to go. So now, using pretty much everything that we've done so far, we're going to calculate the Maxwell limits of integration as well as estimate the water vapor pressure at a certain temperature using parameters of SRK and the general equation of state, cubic equation of state in terms of the compressibility factor. So what I've done here is I've just given us a few constants to take care of. And if I look at my second monitor, what I have is a bunch of things that we need to take a look at here. So one of the first things that we want to look at is the fact that we have these van der Waal equation, I guess, properties, and we have a separate set of them for our SRK equation of state. So what we're going to have our code do is we're going to have to take that and create our own function that separates these out depending on which one we want, right? So if we define a function that is called calculate ABES for our A coefficient, B coefficient, epsilon, and sigma, and we have inputs of our, let's see here, where we want to have inputs of our temperature and the equation of state type that we're using. So for EOS, we're going to be using SRK to go ahead and try and get those variables in our function here. So now, one of the first things we want to do here is we want to calculate the reduced temperature, which was just defined as a temperature which is scaled upon a certain substance's critical point. So the reduced temperature, I'm going to label that TR, is going to be equal to the temperature that we input divided by the critical temperature, and that's going to give us the proportion between that. So that's the first thing we need to do. Now after that, I'm going to pull up my list of values here now. We're going to go ahead and create a dictionary of sorts for our multiple values, right? So the things that we have to calculate right now, if I take a look, we have to calculate S, we have to calculate E, we have to calculate omega. I'm going to just list that as O. Calculate psi, so I'm going to get P. We need to get our compressibility factor. So that's going to be, actually we don't really need that. And our alpha, so A. Alpha, as well as our A and B values. Right? So in order to initiate our dictionary, what we're going to do is have our two entries, which is going to be van der Waals, which is going to be equal to something based on that. And we're going to have our SRK, which is going to be the same thing. Come on. Now for our van der Waal equation, sigma is equal to 0, as I see. So that's going to be the entry for that. And for the SRK equation, sigma is 1. And after that, what we need to do is we want to put our square brackets in EOS so we know what input it depends on. Let's see, make sure everything is good here. Expression cannot be assignment target. Interesting. Why is it giving me that? Oh, not an equal sign. We have to use a colon to designate these. So use a colon, all should be good. And now we do the same thing for the rest of these basically. So we're gonna have our van der Waal, and it's for our epsilon, van der Waal is 0. For SRK, van der Waal, or the epsilon is also 0. EOS. For omega, our van der Waals is going to be omega is going to be 1/8. And for SRK is going to be, let's see here, it's going to be 0.08664. So 0.08664. For our psi value, for van der Waals, it's going to be 27/64. So van der Waal 27/64. For SRK, it's going to be 0.42748. 42748. All right. For EOS, double check that I put that in right. 42748. Yep. Okay. For alpha, now for van der Waals, alpha is equal to, it's just equal to 1. However, for our SRK function, it's going to be an equation that we have to input. So let's go ahead and get that. So the equation that we have to input here is going to be 1 plus, and in parentheses, 0.480 plus 1.574 times W, and that W is coming from up there. So 1.574 times W minus 0.176 W squared times W squared. And that parentheses, and then multiply, start a new parentheses, 1 minus the reduced temperature, the square root of the reduced temperature, 1 minus TR to the 0.5 power, means the same thing. And that should all be to the second power. Just double check my parentheses. Yep, that should be good. So that's how we define that. Now for A and B values, these are just equations that we're going to be using. So for our A value, the equation is P times R squared times the critical temperature squared. So TC squared all over, so all over the critical pressure, PC. And for our B value, it's going to be omega times R times omega times R times the critical temperature all over the critical pressure, right? And we want to return A, B, E, and S. So that should pretty much do it for all of our A, B, E, and S retrievals based on our equation of state that we're using. And so the next part is going to be getting these values into the general equation and calculating that through. So now the next step here, we're going to define another function, and we're going to call this cubic p, because we're going to be using the we're going to retrieve those values based on our volume, temperature, and equation of state, which we're going to be using SRK for right now. And we're going to use those to go ahead and calculate the pressure at a certain temperature. So let's go ahead and call our ABES retrieval function. So A, B, E, and S are going to equal calc ABES with inputs of temperature and EOS. And we're going to return the general equation of state, which is going to be RT, R times T, over V minus B, right, minus A divided by V plus epsilon B, EB, times B, V plus S times B. And yeah, that should be that. So this is going to go ahead and give us the pressure at that certain volume temperature using the EOS. Now the last thing that we need to do here is we're going to define one more function, and we're going to call this the Maxwell areas. Maxwell areas, and what we're going to take in is we're going to take in P, T, and the EOS, which is going to be equal to SRK, of course. So first things first, we want to go ahead and get our volume of the liquid, volume in the intermediate, and volume in the gas, which is going to be equal to the cubic volume, the roots that we're going to use. So it's going to be cubic V of P, T, and the EOS. And so after that, how we're going to return this is we're going to use something called the quad that comes from the SciPy integrate library, sub lambda. So this is going to give us our equal constructions. So it's going to be the lambda V colon, and the first one we're going to do is we're going to get the P minus the cubic P of the V T EOS with a subcat of 0. And we're going to also do kind of the same thing, except it's going to be the other way around to get the other area. Limits of integration. We also need limits of integration. So our limits of integration are going to be from the bottom, which is the liquid, to the intermediate. And we're going to do a similar thing here, so I'm actually just going to copy paste the rest of this here. And instead, we're just going to go the other way around with this. So it's going to be the cubic pressure minus the input pressure. And we're going to go from the intermediate volume to the gaseous volume at 0.